Hello and welcome to another video. In this video, we're going to be working on kth smallest in lexicographical order. And it's very similar to yesterday's problem, except they're just asking for something else, so I'd recommend doing yesterday's before doing this one. So here you're given two integers n and k, and you want to find the kth lexicographically smallest integer in the range I to n, or 1 to n. So here, 10 is the second smallest. And so hopefully you should know what lexicographically smallest means by now, but in this case, it's kind of the same as letters. So like a space is better than anything else, and then a smaller digit is better than like a bigger digit. So for example, this is better than this, even though this is bigger. This is lexicographically smaller, because wherever you have a difference, the smallest number is going to be lexicographically smallest. Kind of the same thing as just like characters in a word, you could think. So yeah, so here it's this, and here it's this. And we can't just like build the thing like we did yesterday and then just find like the kth in the array, because this is too big. So we need something better. So I'm actually gonna use this image from the editorial. It's quite good. So I don't have to draw out these nodes to demonstrate like what we have to do. So let's say n is 99 and k is 50. So we want the 50th smallest number in this whole thing, and here's all the numbers. So we have 1, 2, 3, and then I just don't show the 4 through 8. And then from 1, you have like 10, 11, and so on. So what's like the order of the lexicographically smallest? So 1 is the smallest, then you multiply by 10, and then if you could multiply by 10 again, but that would be out of range. So it's actually going to be 1, 10, all the way through 19, and you come back here, and then all of these, and then you go here, all of these, then 4, then all those, and so on, and so on, and so on. But this tree might get like really big. There might be a lot of levels, and we can't go through these one at a time. So instead, what we can do is we can count up the number of nodes at the tree rooted at our level. So count up nodes at tree rooted at our level. And how can you do this quickly? Like we can't build them all, but what we can do is we can have 2 pointers. One is going to be our current level, and then the next is going to be the level right after. And the level right after our current node. So if we're at like, if our root is x, the one right after is just x plus 1. And then what we can do is we can basically just say, okay, let's just keep going down this tree until the node we have is out of bounds. And for every level, how many nodes are there? Well, it's just the one after minus ours plus 1. Actually, I don't think there's a plus 1. Yeah, I don't think so. So like in this case, there's just 1. So at this level, there's 1 node. And then you would go down to the next, and you would check in both of them, and you would check like, are we still less than 99? Yes. So we'd go down to this one and go down here, and then we say how many are at this level. So it's 20 minus 10, so there's 10. And then we'd go down again, and that would make it 100 and 200, and then we say we're out of bounds, so we're done. So essentially, at the tree rooted at 1, there are 11 nodes. So we can write that down. So there's going to be hard to. Okay, so at this tree, there's 11 nodes. And we can do this really quickly because we just go down one level and in O of 1 check how many nodes are at this level, then the next level, and so on and so on and so on. So there's 11 nodes here. And we wanted the 50th. So we have kind of 2 options. Do we want to go down our tree, or do we want to go to the next tree? And also keep in mind, like if n was like 15, then like the maximum isn't always going to be this minus this. It'll be this minus this, or if n is smaller, we're going to have less. So if n is like 15, then we would do 15 minus 10 instead. Okay, so there's 11 nodes here, and like I said, we have 2 options. We can either go down a level, or we can go across. Well, we want to go across because there's only 11 nodes here, so going down, it's obviously not here. It's going to be over here. So when we go across, what we need to do is we need to say there's 11 here, we're going to the next one. That means we skipped 11 nodes, so we could decrement here. So we could say now there's 39 nodes left. Now, for this level, let's do the same. Let's do the 2-pointer thing. Let's calculate how many nodes are here. So it's going to be the same exact thing here because this is identical. So there's 11 nodes here. So we can write that down, 11 nodes. So do we want to go down or do we want to go across? Well, we want to go across again. So we have 28 left. And then we go to the next level. How many nodes are here? There's 11 again, because it's the same exact thing. Now, like I said, they won't always be the same because n might end earlier, but in this case, it is the same. So there's 11. So do we want to go down or across? We want to go across. There's 17 left. So let's just quickly draw another one. So at node 4, and all the nodes below that guy, there's 11 as well. And so we have 6 left. And then finally at node 5, let me actually draw that. So we'll be at node 5 with 6 nodes left, but there's 11 here. So then we want to go down. And how much does it cost us to go down? Well, if we go down, all we're skipping is just the one node we're at. So we just decrement by 1. So we have 5 nodes left. And then at 5, what are all the nodes? So it's just going to be, it's just going to be 0, 1, 2, 3, 4, and so on. So it'll be like 0, 1, 2, 3, 4. And then this will just be like this, right? So 5 is going to this, going to this, going to that, going to that, and then going to this. And so as we go down to this level, so when we go down to this level, we're actually going to be here, right? And then when we're calculating like how many nodes are at that level, like at 50, that we're going to get 1 here. So if we get 1, then we can't go down, so we have to go across. So we would go across to 1, and then we would, I didn't even know they made this arrow thing, and then we would subtract 1, so 4. And then we'd go to 2, and then we'd subtract 1, so 3, and so on. Then you'd go over here, subtract 1, 2. And then you would go over here and subtract 1, 1. And once k is 1, now that's like your smallest node, so you're done. So essentially, that's going to be our algorithm. So to recap, we count nodes at current root. If it's less than k, decrement k, and go across 1. If greater than or equal to k, move down a level, and decrement k by 1. And so wherever you end up, that's going to be your answer. And we can get these things really quickly because for a given node, we can get the whole thing in log n time. So if from like 1 to 1,000,000, we can get that whole thing in log 1,000,000. Because we're essentially multiplying by 10 every time. So it's actually log base 10. It's even faster than like the normal log base 2 for most of these. Okay, so we want a helper function to count the number of nodes at a level first. So let's do that first. So we'll say private int count nodes from root or something, or in tree. And we're going to give it the root and the n. And so the current will be, or I guess we'll just say current is root, and next will be current plus 1, right? Like the subtree to the right of it, just current plus 1. So, and we'll have a result. So while current is less than or equal to n, we still have nodes to count. Or yeah, so we're going to add to the result. So like I said, we can either subtract the next guy minus our guy, or if that next guy is, like if we go back here, like let's say n was 15, we wouldn't do 20 minus 10, we would do 15 minus 10. So we subtract whatever's smaller, this guy or this guy. And if it's this guy, then we have to include that value as well. So we're going to say n minus current plus 1, because we have to include those. Like if it's 15 to 10, we include all those. But if it's 20 to 10 and 20 is in the next one, then we don't include that. So it'll be next minus current. So we're going to add whatever that is. And then we're going to multiply both our things by 10 until we're out of bounds. So 10 and next 10. And we just return the result here. Okay, so now what we need to do is we need to say int cur. So we start out at 1, and we need to say while k is greater than 1. We want k to be 1 because that means it's currently the smallest. So we're going to say int nodes equals count nodes in tree. So we're going to give it cur and we're going to give it n. And so if there are more nodes than k or equal, then we have to go down a level. So if nodes greater or equal to k, then we have to go down a level. So remember, to go down a level, we just subtract 1 from k, because all we're getting rid of is our current value, and that's it. And then to go down, we just multiply it by 10. In the other case is we're actually moving across, right? Like if we're here, we're moving across here. Or actually, we're not doing that. So like if this is our tree, we're moving from here to here. So then we have to subtract this whole tree from k. So that means k minus equals nodes. And then we have to go to the one to the right, which is current plus 1. And then we just return the curve here. Or, yeah. Okay, so let's try to run this. Okay. And we got problem. Okay, so we're saying it's 3, it should be 2. Do you screw anything up? So, okay. So if nodes is greater than k, then we need to go down. Otherwise, we go across. Oh yeah, we need to accumulate this. So let's try again. Okay, so yeah, so anytime you get stuff like this, when numbers are massive and your result is wrong, it's almost always overflow. So we can just change everything to a long. So long, and this can be long. Result can be long as well, I guess. Yeah, just make everything long and then just return later. So this would be long. And yeah, so this cur now is a long, so we can just convert back to an int, because that's what it expects. Oh yeah, and this needs to be long. Okay, I mean, maybe you don't need all of them to be long, but yeah, I don't want to bother figure out which one needs to be which. Okay, there we go. Yeah, it's almost always the case when your numbers are too big and then your stuff is wrong. So, okay, so here, so let's think about like time and space and all that. So essentially here, like every time we compute the number of nodes in a tree, that's log, because every level we can do an of 1, but we have to traverse down. So every time we do that, that's log. And then what are we doing outside? So we're either adding 1 or we are multiplying by 10. But we can't add 1 very many times. Like when we add 1, the most we can add is like 10 times every time. So we're mostly like for every multiply by 10, we're adding at the most like 9 times, which means the add is constant, and then it's mostly dependent on how many times we multiply by 10, and multiply by 10 is log as well. So it'll be log n times log n, or like log squared n. And then let's see the space. So we don't have anything. So it's just gonna be there isn't even recursion here, right? So it's literally just of 1. Yeah, we don't have like a recursive counter, so it's just of 1. And yeah, that's it. So it's gonna be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.